Hello, friend or Chemistry 1 students. Here are your Chapter 13 notes for Day 2. This is starting at atomic orbitals on your outline and finishing out Chapter 13, Section 1. So, we're going to start with, remember we were talking about the quantum mechanical model. And we're talking about these different models of the atom. And we really are concerned about where the electrons are, because all of the chemistry that happens is because of what the electrons are doing. So the reason certain reactions take place and certain bonds form is because of what the electrons are doing. It's all about the electrons. And so it's really important that we know where the electrons are in an atom, because it allows us to predict what's going to happen. So we were talking about this quantum mechanical model, which was a probability. What's the probability that we're going to find an electron within a three-dimensional volume of space around the nucleus of an atom? So this quantum mechanical model, okay, solutions to the Schrödinger equation gives the energies or energy levels an electron can have. So this is sort of how the quantum mechanical model is similar to the Bohr model, right? Bohr said that when an electron was in a particular energy level, it had a particular amount of energy. It was quantized. And when you solve Schrödinger's equation using calculus and such, one of the things that you get is how much energy an electron can have. For each energy level, the Schrödinger equation also leads to a mathematical expression describing the probability of finding an electron at various locations around the nucleus. These various locations around the nucleus, this is called an atomic orbital. And an atomic orbital is represented pictorially, which just means as a picture, as a region in space in which there's a high probability of finding an electron. So Schrodinger equation, okay, the solutions to it kind of lead to two different things. They lead to knowing how much energy an electron has, a specific amount, so a quantized or specific amount. And it also leads to the probability that you're going to find an electron within a various three-dimensional space around an atom. And again, that was part of what was wrong with Bohr's model, is if you think about the solar system, it's flat. You can draw the solar system flat, and an atom isn't flat. Okay, so the quantum mechanical model really is thinking about this atom as a three-dimensional atom. So the energy levels of the electron in the model are labeled by principal quantum number. Which are kind of abbreviated with an N. Now, these principal quantum numbers are assigned values of N equals 1, 2, 3, 4, etc. So these principal quantum numbers are a whole number. And for N equals 2 or more, there are several sublevels with different shapes and at different amounts of energy. So this sublevel is called atomic orbitals. So another way to kind of define an atomic orbital is to say that it is the energy levels within a principal, and sometimes I refer to it as a main, okay, energy level. Now, these sublevels, okay, each energy sublevel corresponds to one or more orbitals of different shapes. And these different atomic orbitals the orbitals describe where an electron is likely to be found. So we have these main or principal quantum numbers which correspond to energy levels. Okay? And within these energy levels are sublevels. Okay? And within these sublevels are orbitals. Now, one of the things about this, I'm going to bring in a picture of the periodic table. So these n numbers, okay, correspond to the periods on the periodic table. So these are our n numbers. Okay? So each period on a periodic table is a different principal energy level. Okay? So part of what we're going to kind of talk about today is the fact that our periodic table doesn't look the way it does by chance. It looks the way it does on purpose. So, I think we already talked about that. So I'll erase that. Sorry. Okay. So, again, this idea here is we have this principal energy level, which has a sublevel, which has an orbital. Okay? So, we know that we already talked about the fact that each energy sublevel corresponds to one or more orbitals of different shapes, and that the orbitals describe where an electron is likely to be found. And again, why are we so concerned about electrons? Because all of the chemistry that takes place between atoms is because of the interactions and movement of electrons. So these different atomic orbitals are denoted by letters. So we have the S sublevel with the S orbitals, which are spherical. So by spherical, we mean that they look like a basketball, right? They look like a round ball. So the idea is the nucleus would be inside in the middle of that round ball, and this S sublevel surrounds it. Now again, why do we say it's spherical? Remember, that's that 90% probability. So 9 out of 10 times you would find an electron within that spherical shape. 1 out of 10 times you would find that electron outside of that spherical shape. So again, what you're kind of saying by the fact that this is a spherical shape is that the probability of finding an electron at a given distance from the nucleus doesn't depend on the direction because of its spherical shape. So there's no difference in probability above the nucleus or below the nucleus or in front of the nucleus or behind the nucleus. That probability is the same everywhere within that sphere. The other thing about the s orbitals is that there is only one s orbital within an s sublevel. So they're all with letters. So the next one we're going to talk about is the p sublevel. Okay. With the p orbitals, which are dumbbell shaped. So again, we often kind of draw them kind of looking like an infinity sign. But again, remember, they're three-dimensional, so think about a barbell, like a weight, and how it's small in the middle and would be bigger on its ends. There are three kinds. Okay. There are three kinds of p orbitals that have different orientations in space along the x, y, and z axes. Now, you're probably pretty comfortable, right, from math class with your y-axis and your x-axis. But again, an x and a y-axis means that something's flat, and atoms are not flat. So there is a third axis. And in chemistry, we often kind of draw it sort of like this, meaning that it's kind of going in front of and behind. So one way to kind of think about this is if you take three pencils, right, and you make your x-axis and your y-axis. Now you're going to add that third pencil, and your z-axis is going to stick out in front of and go behind that flat x and y axis. So that's that third orbital. And what we're talking about here is that these orbitals that look like dumbbells are located on this x, y, and z axis. So kind of two of them are flat and the other one's kind of sticking out at you and going back behind. And there are three p orbitals. So the next name of the atomic orbitals, or the sublevel, okay, is the d sublevel, with the d orbitals, which are mostly cloverleaf shapes. Oops, clover. Okay, 4 of the 5 are. So what we mean by that is, right, they kind of look like a 4-leaf clover. Okay, so they have that kind of cloverleaf shape. And there are 5 d orbitals within the d sublevel. Lastly, okay, there is the f sublevel with the f orbitals. And for their shape, we just say that they are more complicated. Okay, and in fact, there are 7 F orbitals within a F sublevel. Now, each orbital, okay, can hold 2 electrons. So we're going to take a look at something, okay? So it's going to get hard to read this. So again, we're going to take a look at that periodic table. Because again, the reason the periodic table looks the way it does is because of the quantum mechanical model, right? We said that the S sublevel has 1 orbital that'll hold 2 electrons. Notice we have 2 tall columns here on our periodic table. Okay. We said that the next energy level was the P sublevel. The P sublevel has 3 orbitals, each holding 2 electrons, which makes 6. Notice 1, 2, 3, 4, 5, 6. 6 tall columns over here. Next, we talked about the D sublevel. And we said that the D sublevel has 5 orbitals, each holding 2 electrons, which makes 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You guys, this is not a quinky dink. Okay, your periodic table is telling you way more than just element names, symbols, atomic mass. Okay, lastly, right, there's the F sublevel with 7 F orbitals, each holding 2 electrons, which is 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So what we're going to talk about over the next couple days is the fact that these first 2 tall columns of the periodic table that I kind of made yellow here, in these 2 columns, we're putting electrons into the S orbitals. These 6 columns to the right that I made red, well, there we're going to be putting electrons into the P orbitals. These 10 short columns in the middle of the periodic table, in there we're putting electrons into the D orbitals. And finally, these 2 rows of the periodic table that we have pulled out and that we've put down underneath, in here we're putting electrons into the F orbitals. So your periodic table doesn't look the way it does by chance. It looks the way it does because of what we know about the quantum mechanical model. So, in terms of energy, because remember all of these different sublevels and orbitals have a certain amount of energy, okay? P sublevels are higher in energy than S sublevels. All 3 P orbitals, because remember there were 3 of them, have equal energy. Next, we're going to talk about the D sublevels. The D sublevels are higher in energy than the P sublevels. All 5 d orbitals have equal energy, right? And lastly, you probably are able to predict this now a little bit, right? The F sublevels are higher in energy than the D sublevels. All 7 F orbitals have equal energy. So if we're going to go in order from low energy to high energy, the lowest sublevel in terms of energy is the S. Next are the P. Next are the D. And finally we have the Fs. That's what this is saying. And it's saying that when we have these 3 different p orbitals lying on that x, that y, and that z axis, all 3 of them have the same amount of energy. So when an electron is in an x orbit, a p orbital that's on the x axis, or a p orbital on the y, or a p orbital on the z axis, it's that electron in all of those different places still has the same amount of energy. So that brings us to a chart that talks about this principal energy level, which remember corresponds to a row or a period of our periodic table. So when n equals 1, we can only have one sublevel. And because the S sublevel is the lowest type of energy, the type of that sublevel is going to be an S sublevel. Now remember, an S sublevel only has one orbital. And an orbital holds 2 electrons. So the maximum number of electrons is 2. Now when we get into n equals 2, we can now have 2 sublevels. Which type? Again, always an S because that's the lowest, and a P. Now, again, remember, an S sublevel only has one orbital, but a P sublevel has 3. So, to get the total number of orbitals, I can have 4, the 3 P's and the 1 S. Each orbital holds 2 electrons, so that means I can have 8 electrons total. When n equals 3, I can have 3 sublevels. Which ones? The S first, because it's the lowest in energy. Then the P, because it's the next lowest in energy. And now the D, because it's next. An S sublevel again has 1 orbital. The P has 3. The D has 5. So I add those all together. I get a total of 9 orbitals. Each orbital can hold 2 electrons, so I can have 18 electrons. So when I get to n equals 4, I can have 4 sublevels. Which ones? The S again, the P again, the D again, and now an F. An S has 1 orbital, a P has 3, a D has 5, and F has 7. So again, I add those all together, and I get a total of 16 orbitals. Each orbital can hold 2 electrons, so that gives me a total of 32 electrons. Now, I want you to look for relationships here. Right? So when I have a principal energy level, oops. Okay. So in my principal energy level, my N is equal to my number of sublevels. Right? Notice my N is the same as my number of sublevels. All right. How do I figure out, using my N, the total number of orbitals? So using my N, how do I figure out my total number of orbitals? So what's my relationship between this and this? This and this. This and this. This and this. Maybe you noticed that it's equal to N squared, right? 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. So guess how many total number of orbitals I could have when N equals 5. Hopefully you said 25. Lastly, how do I figure out, using my N, the maximum number of electrons? So what's my relationship this time between my N and my maximum number? Well, remember, each orbital can hold 2 electrons, so it's 2N squared. So again, we're starting to kind of preview here that because of what we know about the quantum mechanical model, that has a lot to do with the way the periodic table looks. It looks the way it does because it helps us know what orbitals we're going to be putting electrons into in these atoms. So that brings us to your homework, which is on page 366, questions 2 through 4. You can type those up or handwrite them, and you will submit them for the assignment in Google Classroom. Have a good evening.